All right, we have Chapter 4, Section 1, Day 4. Use inverse trig to find a missing angle. So if you're just given the side lengths and angle theta, and you're trying to figure out what is the value of the angle, you use inverse trig. So in words, we have inverse sine, and I put the E on the end because that's the word sine. And on the calculator, you see sin to the negative 1. It's inverse sine. So if you look here at the sine button, just above that in blue letters, sine to the negative 1. So to get to that, you press second sine, and then you would type in your problem. But since it's not really truly an inverse, it has its own name, arc sine. And sometimes you might see this, like this other calculator, where there's sine. It has a sine instead of inverse sine, which is actually a better descriptor. Because, for example, you know how when you have the parent function, the quadratic parent function, x squared, and you have a parabola, and then we say the inverse of x squared is square root x, right? But that graph is just like this. It's not the whole inverse. It's the inverse if we restrict the domain. Like if we take x squared and we cut it off and we just look at the positives, then it's the inverse. It's the inverse of a restricted domain. Because if we truly did it inverse, we would have the negative values also, but we know those are imaginary if we did the square root of the negatives. So we just kind of ignore that. But technically, it's not an inverse. It's the inverse with a domain restriction. So the same is true for sine, cosine, tangent. It's not truly an inverse because we'll have to do a domain restriction. And we'll talk about that later when we get into graphs of these functions. So it has this other name, arc sine, which includes the domain restriction. All right, so we inverse cosine. That's in words. The button on the calculator, cos negative 1, and that's arc cos, or arc cosine. And then the same for tangent. Inverse tangent, on the calculator, tan to the negative 1, inverse tangent, or arc tan. All right. And we're going to do an example. So if you're given this triangle, it's a right triangle because this section is right triangle trig. And it's giving you an 11 right there, and a 26 right here, and a theta right there. And then it says find theta. So the same as we started all the other trig problems, we should start by trying to figure out which one are we dealing with. Sine, cosine, or tangent. So we can label our triangle pieces that we have. We know that's theta. And opposite of theta is the opposite side of the triangle. The other leg is the adjacent leg. And I'm not really worried about the hypotenuse across from 90 because there's nothing over here. There's not an x, there's not a number, there's nothing there. I don't care about it. So then I write out my SOHCAHTOA. And I look to see what I have in my problem, and it will narrow down which one I'm going to use. So whenever I don't have the hypotenuse, I find the easier way is look for the one that doesn't have an H. Well, this one has an H, so it's not that one. This one has an H, so it's not that one. This one does not have an H. It has an O and an A. It's an O and an A. So tangent, this is going to be a tangent problem. So I can set this up as, I'm going to go ahead and write the original one. Tangent theta is equal to opposite over adjacent. So 26 over 11. Okay? But I want to find out what the value of the angle is that would give me the side lengths 26 and 11. So I can do the inverse tangent. So I can switch this around. This is the short version. I'm going to show you more of a proof example in just a second. So if I want just the theta, that means I'm going to write theta, and I'm going to do the inverse tangent of this number. So inverse tangent of 26 over 11. So then I go to my calculator. You can see it. And I want to make sure I am in degree mode since I'm dealing with degrees. We haven't talked about radians yet. So mode, yes, degree is highlighted, so I'm good. Second, quit. I want to do the inverse tangent. So there's the tangent button, but I have to do second tangent. 26 divided by 11. And it gives me 67.067, I'm going to call that 9. When we're dealing with degrees, let's always round to the whole degree. We don't want decimals inside the degrees. So theta equals 67 degrees. Make a note that. Always round to nearest degree. Okay. So the reason I can just do the shortcut method here, where if I have tangent theta equals a ratio of sides, and I know I want theta, I can just jump to theta equals the inverse tangent. So if I do an example of that, so we'll just call this a proof example. It's not exactly a proof, but close enough. Proof example. So this is just a made-up thing. So if I had sine of theta equals 2/3, and if I want to find out what this value is, I need to get rid of sine. So I'm going to go back to my x squared square root. So if I had x squared equals a number, and I wanted to get x by itself, I would do the square root. I would do the inverse operation to get rid of the squared. So the inverse operation of sine is inverse sine. So I'm going to do sine, inverse sine of theta equals, if you do something on one side of an equation, you have to do the same thing on the other. So sine inverse of 2/3. And since inverse sine and sine are inverse operations, they cancel, and it becomes theta equals sine inverse 2/3. So that is just to show you what I did when I did it over here. I'm not requiring that you show this step every time, so that's why I wanted to show it that way first. So this is my true example. This is just a side note of what I did in between right here. All right. So your assignment, I'm going to say homework, but I don't really mean homework. I mean do it right now work, is page 227. Numbers 31 to 37, all of them, and number 55 and 56. That is not that many problems. Don't, oh my gosh. Come on, you're good.